Welcome back to another STEM with Miss Dubois video. In today's video, we are discussing simple machines. So, this is what today's video will cover. Obviously, it looks quite a lot. So, for that reason, each of these videos will be segmented below in like that YouTube timeline thing, or they will be their own videos in case you want to watch a specific part, and all of those videos will be linked below. What is a simple machine? A simple machine is something that makes the amount of work something or someone does easier. And there are 6 types of simple machines. There is the inclined plane, the wedge, the screw, the lever, the pulley, and the wheel and axle. But before we get any further into the video, let's focus on this bolded word, work. And that is because it is a key part in understanding simple machines and why we have them. So, what is work? Work is how much energy it takes to move an object. And there's an equation for it, which is work equals force times distance. But this is a complicated equation, so let's break it down. Work is measured in joules. Joules is the unit for measuring energy. And joules can do this because work is the act of moving energy from one object to another. Basically, you're measuring another idea of energy. Force is a push or pull on an object, and it's measured in newtons. Distance is how far an object moves, and it's measured in meters. Now that we've broken down the work equation, let's rephrase the definition of work. Work is how much effort it takes to move something. Effort is the energy, which is shown in joules, and work is measured in joules. Moving something requires a push or a pull, no matter how you do it. And that is the definition of force. How far something moves is the distance. So you might be wondering, how can we tell if a simple machine works? We can do that by determining the simple machine's mechanical advantage. Now you might be wondering, what the heck a mechanical advantage is? Basically, it's how effective a simple machine is at making work easier. So when a simple machine is used, it poses the question, would this task be easier if this simple machine didn't exist? Now, how do we measure that? Well, there's an equation for it. Duh. This is a physics topic, and physics loves equations. I wish I was being sarcastic, but I swear I'm being very genuine right now. Physics does love equations, and this is a physics topic. So, what are the equations for a mechanical advantage? Well, every simple machine sort of has its own equation, but they all equal these 2 equations because there's actually 2 types of mechanical advantage: the ideal mechanical advantage and the actual mechanical advantage. Ideal mechanical advantage equals input distance divided by output distance. Input distance is how far or how much you move the machine. Output distance is how far the load moves. The load is the object or thing that you are trying to move. As for the actual mechanical advantage, that equals output force divided by input force. Output force is how much force the machine applies to the load or the thing you are trying to move. Input force is the force you apply to the object. There are pros and cons to both equations. For the ideal mechanical advantage, the pro is that it's easier to calculate in a lab, and it can be calculated in advance. The con, however, is that it's not realistic for the real world because it doesn't include things like friction or resistance in its equation, when those 2 things are very, very real in the real world. For actual mechanical advantage, the pros and cons are opposite sort of in terms of how they work. And you'll see this in a second. For actual mechanical advantage, its pros are that mechanical advantage is more accurate in the real world because it includes things like resistance and friction in its equation. However, its cons are that force can be difficult to calculate in a lab without proper equipment, and you can't calculate actual mechanical advantage in advance. You have to do it after collecting data. So you might be thinking, Miss Dubois, you didn't answer my question. I'm still wondering, how can we tell if a simple machine is effective? Well, you have to use those equations to calculate if a simple machine is effective for you. In some way or another, all of the equations I mentioned still kind of follow this rule. If the mechanical advantage is greater than 1, the machine applies more force to the load than you do. The machine does more work to the actual object than you do, basically. If the mechanical advantage is equal to 1, there is no change in force, just a change in direction or distance. If the mechanical advantage is less than 1, You need to put more force on the object, but the task gets done faster. Remember, mechanical advantage is how effective a simple machine is at making work easier. That leaves some room for debate on what you, the engineer, thinks is best. What is an inclined plane? An inclined plane is basically a ramp, and the goal of an inclined plane is to bring objects to higher positions. Examples include ramps, escalators, and staircases. And now remember, inclined planes do make things easier because imagine carrying something up a ladder that is all vertical. That could not be me. So I'll take inclined planes any day. Now, what is an inclined plane's mechanical advantage? The ideal mechanical advantage for an inclined plane is the slope of the inclined plane over its height. To measure the slope, you're essentially measuring the distance of the slant, and the height is how tall the inclined plane is. The actual mechanical advantage for an inclined plane is the load's force divided by the effort's force. The load's force for inclined planes is the weight being raised. The effort's force for inclined planes is the force used to push the object up the inclined plane. A wedge is something that splits things or holds things together. It's basically an inclined plane that moves. Examples of wedges include axes, knives, cruises, or ships. And as for something where a wedge holds things together, an example of that is a doorstop. What about a wedge's mechanical advantage? Its ideal mechanical advantage can be measured by its length divided by its thickness. Thickness is how wide it is at its widest point, basically, and the length is how long the wedge is. For the actual mechanical advantage, its formula is similar to the inclined plane, where it's load's force divided by the effort's force, except this time the load's force is the force pushing the material apart, and the effort's force is the force used to drive or put the wedge into the object. A screw is an inclined plane that is literally wrapped around a cylinder. Its main functions is to dig holes, hold things together, or lift things. Examples of screws include a screw, an auger that is used for like digging holes, drill bits, a jet engine, and a spiral staircase. How do we calculate the mechanical advantage of a screw? To calculate the ideal mechanical advantage, you multiply pi, or 3.14, times the diameter, and then you divide that by the screw's pitch. You find the diameter of the screw by measuring the diameter of it at the bottom, and its pitch is basically the distance between two threads. I'm like oversimplifying that, but you kind of get the idea. To find the actual mechanical advantage of the screw, it's the load's force divided by the effort's force, as we've seen before. But for screws, the load's force is the force separating, lifting, or joining an object, and the effort's force is the turning force applied to the screw. Now it's time to move to a lever, which is a rod that rotates around one point. That one point is known as the fulcrum, and the fulcrum does not move. The purpose of levers is primarily to lift things, like that's its biggest function. But there are levers that cut things or open things. And even when we think about opening things, like a lever opening things, it's technically lifting that thing up just by creating an opening between whatever that object was on and the object itself. A lever's primary function is to mostly lift things, though, and I really want to emphasize that. And there are three types or classes of levers. There is a first class lever where the fulcrum is in between the load and the effort. The effort is the force that you are applying, and the load is always the object being moved. So think of it like this, because I've mentioned these words quite a bit throughout this video. The load is the object that you're moving, always, because you're loading it on to this simple machine. The effort is the force that you, the person, are putting onto the simple machine. Think of effort as you are putting it in, so you are giving it effort, or you are using effort. Think of load as you are loading it on, like you are piling it on. Now that we have that out the way, in a first class lever, you can see the fulcrum in the middle, and examples of first class levers include seesaws and crowbars. The second class lever is where the load is in between the fulcrum and the effort. So where you pile the stuff on, where you put the machine on, that load is in the middle, and the effort is on the end, and the fulcrum is on the way other end. Examples of second class levers include a stapler, and a wheelbarrow. A third-class lever is where the effort is between the fulcrum and the load. And as you can see, the fulcrum is on the end and the effort is in the middle this time around. All right, so let's look at it like this, okay? The fulcrum is the point that the rod turns around, like pivots around basically. The load is the thing that you are trying to move, the whatever it is, right? It could be a baseball. Effort is the work that you are putting in. You are giving that effort. So the effort for a third-class lever is in the middle because you are kind of, or whatever force is being applied is going to be in the middle of the fulcrum, the thing that the rod pivots around, and the load, the thing that you want to move, the object that you want to move. You're not moving it yourself, or else you wouldn't be using a simple machine. Does that make sense? I hope it does. Let me know in the comments. Examples of third-class levers include tweezers and baseball bats, with the elbows being the fulcrum, the effort being the hands, because that is where you are inputting your force, and the load being the baseball. The reason why elbows are the fulcrum this time around instead of like the effort is because you're using your elbows to rotate when you swing a baseball bat. You're not actually gaining a lot of force from that. It comes mostly from the lower part of your arm and where your hands are. So naturally that is below your elbows. That is why it is the effort. And the load is the baseball because when you swing a baseball bat, you ideally want to hit a baseball very far. I hope that makes sense. So now let's calculate the mechanical advantage of a lever. The ideal mechanical advantage is the effort arm divided by the load's arm. This means that the effort arm is the distance between the fulcrum and the effort, and the load's arm is the distance between the load and the fulcrum. The actual mechanical advantage of a lever is load's force divided by effort's force. We've seen this so far with every one of our simple machines. But in levers, the load's force is the weight or resistance being lifted, and the effort's force is the force that you apply. So let's talk about pulleys. A pulley is a grooved circular disc that has a rope go around it or slash in that groove, kind of. The goal of a pulley is to lift objects over a vertical path. Examples of pulleys include elevators, cranes, and flagpoles. Now, let's calculate the mechanical advantage of a pulley. The ideal mechanical advantage is simple this time around. The ideal mechanical advantage of a pulley is the number of ropes used in the pulley that's supporting the load. The actual mechanical advantage, once again, is the load's force divided by the effort's force. This is going to be something continuous or the same throughout each of the simple machines. But once again, once you get into that equation, those equations do look differently because to calculate the force of everything is going to require a different equation. But I won't get into that in this video. So in pulleys, the load's force is the weight of the object being lifted, and the effort's force is the force that you apply to pull the rope. The final simple machine is wheel and axles, and the goal of a wheel and axle is to amplify the force of an object or to increase the distance that the force is being applied. Now, it's really important to note that wheels and axles move together at the same angle. Examples of wheel and axles include doorknobs, screwdrivers, and gears. So let's calculate the mechanical advantage of a wheel and axle. The ideal mechanical advantage is the product of the angle and the wheel radius divided by the product of the angle and the axle radius. Since the angle stays the same for both the wheel and axle, this equation can be simplified to what you see, which is the radius of the wheel divided by the radius of the axle. The actual mechanical advantage is the load's force divided by the effort's force. Once again, we've seen this throughout all of our simple machines in this video, but once again, it's a little bit different. In wheel and axles mechanical advantage, the load's force is the force applied to the axle, and the effort's force is the force that you apply to the wheel. And that was today's video on simple machines. I'm STEM with Miss Dubois. Thanks for watching. I hope you have a great day and a great life. Bye!